Okay, I guess we are live. Yep, we are live. Okay, I can hear myself. So, hi everyone, welcome to another class. So, today we'll be learning about um, two algorithms, like one is topological sorting, and after that, how to find strongly connected components in a graph using Kosaraju's algorithm. So, we'll try to understand both of them, like what exactly does topological sorting gives us, or what exactly are strongly connected components, and then we'll try to see the algorithms for them as well. So, firstly is we'll look into topological sorting, because strongly connected components is kind of like derived from topological sorting only, or the first step to Kosaraju is topological sorting. So we'll learn topological sorting first, and then we'll move into strongly connected components, right? So, given a directed acyclic graph DAG, directed acyclic graphs are also called DAGs, with V vertices and E edges, find any topological sorting of the graph. So, find any topological sorting of the graph. So for example, here if we see, topological sorting is valid term for only directed graphs. All right, so it's valid only for low voice. Why is my voice low? Let me just check. It's set to full, so I think it should not be low. Maybe check on your end once. uh, but yeah, topological sorting is only valid for directed acyclic graphs, right? So, the graph should be directed, and it should also be acyclic. So, for example, here 1032, the one denotes the, and what we have to print is, uh, the output one denotes the order is valid. Okay, so you basically have to print 3210. That's a valid topological sorting of this graph, right? So, we have to find the topological sorting. So let's actually take a few examples to understand what exactly topological sorting is, right? So, we'll try to create a graph here. Let's create a graph. Let's say 1 directed edge to 2. Let's say directed 3, something like this. Let's say 4, 5, and both of them like land up to 6, something like this, right? So let's say we have a graph like this. The topological sorting, what does topological sorting means? It's a order in which the vertices can be written such that all the edges are only from left to right. So the edges, it will be a order in which the vertices will be arranged such that the edges will only move from left to right. There will be no edges that will move from right to left. That is called topological sorting. So for example, for the given graph an example, a topological sorting can be 1, 2, 3, 4, 5, 6. Now see this order in which 1 to 2 is from left to right, the edge. 1 to 4 is from left to right, right? 2 to 3 is from left to right, and 4 to 5 is from left to right, and 3 to 6 left to right, and also 5 to 6 is also left to right. So we have all the edges from left to right. So this is a valid topological sorted ordering, right? What can be an invalid ordering? Let's say we order it something like this, that uh, like this: 1, 2, 3, 6, 4, 5. This is invalid ordering because 4, 5 to 6, this will be from right to left. So this is not a valid topological sorting ordering. So all the edges will be ordering the vertices in such a way that is like v1, v2, they will be ordered in this way, v3, v4, such that all the edges will only be from left to right. That is a valid topological sorting ordering. There might be multiple of them. For example, 1, 2, 4, 5, 3, 6. This is also a valid ordering. And again 1, 4, 4, 2, 3 5 4 2 3 5 6. This is also a valid ordering. If you see, for all of them the edges will be from left to right, so all of them are valid topological sorting orderings, right? So what we are given a directed graph, directed acyclic graph. We have to find a topological sorting of that graph. Now note that the graph should be a acyclic graph. It's definitely directed, right? Otherwise in undirected graph there is nothing called topological sorting. It definitely has to be directed. Now why does it has to be acyclic? If it is cyclic, right, if it is cyclic, that means if there is a cycle, then you cannot have this condition, right, that all the edges will be from left to right, because if there is a cycle there will be a edge from right to left and there will be a edge from left to right. So like this condition will be violated, right? You cannot have this condition that all the edges will be from left to right. So that's why it is only valid for DAGs, directed acyclic graph, right? So that's the condition. Okay, now now we know this, that this finding topological sorting, what exactly topological sorting is, or when is it valid, or how what exactly it is. So now let's see how do we find it. So let's actually draw a graph to find this. Let's say 4 3 4 3 2 5 6 1 7 7, and like this, right? So let's say we have a graph like this. Now see here that it doesn't always necessarily mean that one should be the first node in topological sorting or something like that, right? It doesn't mean that we should always be able to find the valid topological sorting ordering. For example, in this a valid ordering will be 4 3 2 6 5 1 7, something like this, right? So this is a valid ordering. So we should always be able to find such orderings irrespective of where one is or where the other nodes are, right? So in this case one is not the first element in the topological sorting, right? So we should be able to do that. So what we'll do is we'll have a simple DFS function, right? We'll have a simple DFS function, but we'll also maintain a stack. What we'll do in the DFS is, let's say we are doing a DFS, so we are in edge U. So what we'll do is, for V belonging to adjacency list of U, and if V is not parent of U, we'll do DFS V. Once that is done, what we'll do is we'll push it into the stack. We'll push U into the stack once we are done with the DFS. So stack dot push U. So what exactly it does is it will visit all the nodes that can be visited from U, and on top of that it will be pushing it will be pushing U on the stack. So for example, let's say we are starting from 1, right? We are starting from 1. So from 1 we can only, also we'll mark them as visited, right? So visited U equals to true, and that as well will do. Visited U equals to true. So we'll start from 1. So 1 will be not pushed into the stack. First of all, we'll go into 7 because there's a edge from 1 to 7. So 7 and from 7 we cannot go anywhere. So 7 will be pushed into the stack. 7 will be the first element to be pushed into the stack, right? So 7 will be pushed into the stack. After that, from once we have visited 7, where did we come to 7 from? 1. So we'll come back, we'll recurse back to 1. So when we recurse back to 1, we have completely explored 1. So we'll be pushing 1 on top of this. Now what we'll do is when we call this DFS, we'll go through all the nodes, right? For I equals to 1 to n, right? And here we'll check if not visited I. If not visited, right? If we have not visited, and then only we'll call DFS, right? So 1 is visited, 7 is visited. Next, what is next in the like if we run a loop, what is next? What is the next element? The next element will be 2. Is 2 visited? 2 is not visited, right? So we'll call DFS2, right? We'll call DFS2. From DFS2 we let's say we are going to DFS5. So DFS5 we go to. From DFS5 we can go to DFS1, but 1 is already visited, so we do not visit it again, right? So DFS5 will push 5 first into the queue. and we come back to 2, right? We come back to 2. Now from 2 we can also go to 6. So let's go to 6, DFS 6. 6 is not visited yet. And from 6 we can go to 7, but 7 is already visited, so we'll not visit it again. So we'll go to 6. Now we come back to 2. Now we have completely explored 2, right? We have completely explored 2, so we can push 2 into the stack. So stack dot push 2 after this, right? And now let's come to 3 next in the list. 3 is not visited yet, so we'll visit 3. And from 3 only one edge is there up to 2. 2 is already visited, so we'll not visit it again, so we'll just push 3 into the stack. And after that 4 is also visited and 4 is pushed into the stack, and we are done with the 5 6 7 8, everything else is visited, right? So we are done with the topological sorting. Now see the order in which they appeared in the stack, right? They appeared in the stack, the order is 4 3 2 6 5 1 7. Is this a valid topological sorting? All the edges are from left to right, right? So 3 to 2 is there, 2 to 5 is there, 2 to 6 is there, 6 to 7 is there, 5 to 1 is there, 1 to 7 is there. So see, all the edges are from left to right. So this is indeed a valid topological sorting ordering. So this is how we'll do. We'll have a DFS function. In DFS, we will first explore all the nodes that can be visited from the current node, and they should come below it. They should come to the right of it in the topological sorting, so, or below it in the stack. Now we'll visit them, we'll push them in the stack, and finally once we have explored the node completely, every node that is can be visited from this node, we will push this node as well into the stack, right? So that is how we'll do topological sorting. So let's actually try to write the code for this. I hope it's clear with everyone. So topo sort v and adjacency list, so we'll take a stack. Let's have a DFS. So we'll have a few things here. So first is vector bool visited, and then stack int x, and void DFS. In the private section only we'll write void DFS int s, right? Int s. So visited s equals to true. Then we'll explore the adjacency list. So we'll also pass here the adjacency list vector int and, or vector int adjacency list will pass the array reference, right? Vector int adjacency list for int v. Also probably we need to or we can do it like here as well. We can maintain the vector int graph okay, let's just pass it as a reference, right? Vector int adjacency list star adjacency list for int v belongs to adjacency list of u if v not equals to, if v not equals to if not visited v, rather if not visited v, we'll do DFS v and adjacency list, and finally we'll push it into the stack. So x dot push s. So for int I equals to 0, int I equals to 1, I less than equal to v, or rather I equals to 0, it's 0 based, so I less than v, I plus plus. And before that we'll also have this visited. So visited visited equals to vector bool of size v, and everything is false initially. So if not visited I, DFS I, we'll call DFS I and adjacency list, right? So finally whatever we have, will have that in an array. So vector int answer while not x dot empty answer dot pushback x dot top and x dot pop. So we'll keep on popping from answer and we'll finally return answer as return the answer. So answer. Let's run this. Adjacency list of hue, sorry, it should be S. So this is working. Let's try to submit this. Okay, so this is working, right? This code is working. I hope that this was clear with you. So what we have done basically, we are doing a simple DFS, but in the DFS we are also storing it in a stack, right? So what we are doing essentially is when we are DFSing for a node, we are finding all the nodes that can be visited from the given node. So in that case, all the edges will be from left to right only, and after we have pushed them into the stack, finally we are pushing S into the stack because the edges will be from left to right, right? So that's how we are doing, and yeah, finally we are getting this answer. So that is topological sorting. Now next we come into strongly connected components. So we are given a directed graph with V vertices numbered from 0 to V minus 1 and E edges. Find the number of strongly connected components of the graph. So we have to find how many strongly connected components of the graph are there. So in this example 0, 1, 2, 3, 4, we see that there are 3 strongly connected components, 0, 1, 2, 3 and 4 alone, right? So what exactly is a strongly connected component? You can think about strongly connected component as a cycle in a directed graph, right? So if a subgraph in a directed graph has a cycle, then that is called a strongly connected component. What do we mean by cycle again? Like if again, like the formal definition of strongly connected components is like if there are two nodes in a subgraph of the directed graph, if all the nodes are can be visited from each other, like from you can visit from U to V and you can also visit from V to U, then that subgraph is a strongly connected component, right? So 0, 1, 2, there is one strongly connected component. If you see, you can visit from 0 to 1, 1 to 2 and 2 to 0. So we have to we can use to find a strongly connected component or the number of strongly connected components, we can use Kosaraju's algorithm. So we'll understand what is that, right? So let's understand first what a strongly connected component is. I've given the definition, but let's understand it more in better way, right? So we have 1, we have 2, we have 3, let's say we have a graph like this. So how many strongly connected components are there? Again, the definition of a strongly connected component is a subgraph of the graph in which it is fully connected and any two nodes that can be visited from each other. So for example, let's consider this subgraph here, right? And let's consider this subgraph as well. If we see, any two nodes can be visited from each other in both of them, right? So for example, 1 can be visited from 3, so the path is 1 to 3 to 1. Again, 3 can be visited from 1 as well, 1 2 3. 2 can be visited from 3, 3 1 2 in that path, and 3 can be visited from 2 using the path 2 to 3. Similarly 3 and 1 as well. So every node can be visited from each other in this subgraph, right? Similarly 4 5 6 7, every node can be visited from each other. So in simple words, a cycle, if a subgraph has a cycle, if a subgraph of a directed graph has a cycle, it is called a strongly connected component, right? So this has a cycle, this is a cycle, so it is a strongly connected component. This is also a cycle, this is a strongly connected component. However, we'll not mix these two, because between these two, if we take this entire graph entirely, all the nodes are not visitable, cannot be visited from each other. For example, we cannot visit from 4 to 1, right? There is no way to visit from 4 to 1, but there is a way to visit from 1 to 4. So it can be divided into two strongly connected components, right? So that's the definition of strongly connected component. Now let's say this edge is reversed, right? This edge is reversed. Now you see that this subgraph that we have, it is not a strongly connected component, right? In fact, all the nodes individually are strongly connected components now, right? So if a sub if there is no strongly connected component, then individual nodes are also treated as strongly connected components, right? So by default, individual nodes will be strongly connected component. And now here, if you see, like, you cannot visit from 7 to 5, right? You cannot visit from 7 to 6 or 6 to 4. There is no way to visit, right? So all of them independently will become strongly connected components. So that is the definition of strongly connected components. Okay, so how do we do this? How do we solve this? So let's just go ahead with the previous example. So let's see if we can undo the things. Yep. So let's go ahead with this example only. So what we'll do is we'll first find the topological sorting, right? We'll find the topological sorting of this graph. So how do we find the topological sorting? We have already seen that. So let's write it down, like let's do it in the stack. So let's say we start from 1. So first of all, 2 will be visited. Although there is no topological sorting, to be like very clear here, there is no topological sorting of this graph, because again, like there is a cycle here, and topological sorting is only valid for directed acyclic graph. But we'll use the same algorithm that we had done for topological sorting. So we'll start from 1. We'll start our DFS from 1. 1 to 2 can be visited. Then 2 to 3 can be visited. Rather, let's go like this. 2 can be visited, then 3 can be visited, 3 to 4 can be visited. So 4 is visited, 5 can be visited, 6 can be visited, then 7 can be visited, right? So 7 is visited, so 7, let's enter 7 first. Then 6, it is visited from 6, then it comes to 5, then it comes to 4, then it comes to 3, then it comes to 2, and finally it comes to 1, right? So again, like this is not a topological sorting, but we have used the same algorithm that we had used for topological sorting. Now once we have that, what we'll do is we'll generate the reverse graph, right? So in this, we are sure that all the edges are from left to right, or the paths that are there here are from left to right, or from top to bottom, right? All the paths will be from top to bottom that we have. So if we also have a path in the reverse graph, so what we'll do is we'll generate the reverse graph for this, right? So what is the reverse graph? So the reverse graph will be like this, all the edges reversed. And here also this will be reversed. Five to 4, so sorry, 5 to 4, 5 to 4, 6 to 5, 6 to 5, and 7 to 6, sorry. So we have generated the reverse graph, right? We have now generated the reverse graph. In this reverse graph, we'll go in the same order in the topological sorting. Now for a given DFS, if we can visit other nodes, that means they are forming a strongly connected component. Why? Because all the paths here from left and right are from top to bottom. Now we have generated the reverse graph, then there should be no path at all. There should be, like in DFS, we should not be able to visit any other node. But if we are visiting any other node, that means there is a path from top to bottom. There is also a path from bottom to top. So that means they are forming a strongly connected component. So what we'll do is we'll run the DFS now from 1. So from 1, what can we visit? We start from 1. From 1 we can visit 3, and then we can visit 2, right? So from 1 we are visiting 3 and 2. So that is forming us one strongly connected component, 1, 3, 2. This part is forming a strongly connected component, right? Now see that we cannot visit 4 anymore. So 1, 3, 2 are removed from the stack. So 1, 3, 2 are removed from the stack. Now 4 is not visited, so 4, this part is not forming a strongly connected component with this part, right? Now we have 4, so from 4 we can visit 7, then from 7 we can visit 6, 6 to 5 and 5 to 4. So this part is also forming another strongly connected component, right? 6, 5 and 4. So these are the two strongly connected components that we form. So again, what will be the algorithm? First is use the topological sorting algorithm. So use topological sorting algorithm. After that, second point will be generate reverse graph. So generate reverse graph, toposort algo, and then 3 DFS on reverse graph. So DFS on the reverse graph, right? So you, in the same order in which topological sorting like algorithm has returned the stack. So that should be the algorithm for and this is called Kosaraju's algorithm. So that will be the algorithm for generating strongly connected components, right? So let's try to do this. Okay. So vector bool visited and stack int x. So first dfs1 int v, sorry, int s and vector int adg, right? So visited s equals to true for int v belongs to adjacency list of s. If not visited v, dfs1 of v and adjacency list, and finally x dot push v, x dot push v, sorry, s. Okay, so we are done with dfs1. So what we'll do here, first of all, visited equals to vector bool of v of size v and false initially, and then we'll do dfs1, yes. So we'll do x dot clear as well. After that we'll do dfs1 on, so for int I equals to 0, I less than v I plus plus, if not visited I, then we'll call dfs1 on I and with the adjacency list, right? Now we'll generate the reverse graph. So vector int reverse graph of size v. So reverse graph of size v. So for int I equals to 0, I less than v I plus plus, for int v small v belongs to adjacency list of v. So there was a edge was from I to v, right? I to v was an edge. Reverse graph will be the reverse of this. So reverse of v dot push back I, reverse of v dot push back I. So we'll generate the reverse graph like this. Now we'll go for the dfs2. So void dfs2, let's write it down here, void dfs2 int s and vector int adjacent. It will be simple dfs again, simple dfs. So visited s equals to true, and for int v belongs to adjacency list of s, if not visited v, if not visited v, and we just want the count, right? We just want the count. So count is number of times we are doing the DFS. Number of times this DFS2 will be executed. That will be the count of the strongly connected components, and we just want that, right? So DFS2 v and adjacency list. So that should be it for DFS2. So we have done the reverse graph. Also we'll reset the visited. So visited equals to vector bool of size v and everything is false initially. Int answer, int scc count, let's call it scc count equals to 0. For int I equals to 0, I less than v, or rather y not x dot empty, int u equals to x dot top and x dot pop, and we can check if not visited u. If not visited u, what we'll do is dfs2 of u with the reverse graph, so rev and scc count plus plus, so return scc count. So that should be our algorithm. So let's run this. Okay, x dot clear. Okay, x dot clear is not there, that's fine, we don't need that. Okay, we are running into a segmentation fault. Belongs to adjacency of v. For int v belongs to adjacency of not visited v, dfs1 v adjacency and x dot push s. So I think this much should be like working fine. So let's return so let's return a 0 here. Let's see if it's breaking before that or after this. Okay, it's breaking before this only, so let's try to do it here. Okay, here it is working. So this reverse graph is breaking. Vector int reverse graph of size v, I equals to 0, I less than v, I plus plus. For int v belongs to adjacency list of v, adjacency list of I, adjacency list of I, and that should be it. So expected is same, so let's run this. Okay, so this is also working fine, right? So this is how you can generate the SCCs. Now if you want to know, like if you want to generate the SCCs, here we have just generated the count, but if you want to generate the SCC, like what are the SCC each of them belong to, in that case what you can do is you can add a label here. Like when you are visiting, you can pass a label parameter here and add that label to this node that is getting visited, right? So that's how you can generate the exact SCCs, like which nodes are forming part of which SCC. So that's about Kosaraju, right? So we have learned about Kosaraju's algorithm as well, and complexity, again it's just 2 DFS that's happening, right? So it will be order of v plus e. So that's the complexity. Okay, so for your homework, what you will be doing is I'll not be giving you graph based questions, but it will be simple tree based questions only. So first is kth largest element in a BST. So you are given a BST, you have to find the kth largest element. Pretty simple question. Second is serialize and deserialize a binary tree. So you have to serialize and deserialize a binary tree. Third is both of them are same, right? Serialize and deserialize, yes, I think both of them are same. Find the closest element in BST. So you have to find, given a BST and an integer, find the least absolute difference between any node and of a node value of the BST and the given integer. So given an integer, you have to find what is the node that contains the minimum absolute difference with, or closest node value with the given integer. So you have to find that closest element. And finally, rotten tomatoes. So you have a grid. This is a grid question, so this is a graph question. So 0 represents empty cells, 1 represent fresh, and 2 represent rotten tomatoes. We have to determine the minimum time required to rot all the tomatoes, right? So we have to determine the minimum time. So there are some rotten tomato cells, and it takes 1 unit of time to spread to make the surrounding tomatoes rot as well. So what is the minimum amount of time to rot all the tomatoes, right? So these are the questions for your homework. Just try to solve them, and I'll be like, again, we'll have the class on Wednesday. So Wednesday I'll be again like discussing 2 more problems, and I'll be giving out a few more for practice. So thank you guys for joining in. I hope that there are no questions on your end. So today we have learned about topological sorting and strongly connected components. So if you are given these questions on these things, I believe that you should be able to do them. So thank you for joining, and good night.